We are given this transformation from the polynomial space Pn into the real numbers, where the transformation of a polynomial is a polynomial evaluated at 0. And so what we want to do is show that this transformation is linear. And so basically that means that we have to show the two properties that it's additive. So that t of, I guess we would say, p plus q equals t of p plus t of q, and that we can pull out a scalar multiple, so t of c times p, where p and q are polynomials, equals c times t of p. So I'll let c be a scalar, so be a real number, and p and q are going to be polynomials. And we don't necessarily know what this Pn is. So we have to show this and show this. So since p and q are going to be in this polynomial space, what we could do is just sort of define them. So I'm going to let p be an arbitrarily defined polynomial in here. So it'll be an x to the n, an minus 1 x to the n minus 1. That's just some polynomial a1x plus a0. And q is going to be, I'll just use b's for my coefficients. Right, so those coefficients can be any real numbers, and that should let them be completely arbitrary within these polynomial spaces. So first of all, what I'll do is show the left-hand side here. So t of p plus q, in this case, is going to be t of, and if I add these two things together, I'll get power of x by power of x. I can just kind of add the coefficients. And I'll get, each of them can just kind of match right together with the corresponding x's. And so that is just going to be evaluated at 0. So it's going to be an plus bn evaluated at 0, plus all the way through. a1 plus b1 evaluated at 0, plus a naught plus b naught, it's a naught plus b naught. And if I do t of p, well, this is going to be an times 0 plus the same thing. It's just like everything vanishes except that last term. So a naught t of q is b's, not a's. Keep writing a's, it's a b naught in the end. And so t of p plus t of q will actually just be a naught plus b naught, which is the same thing as t of p plus q. So that side's good. And so I'll show the one on the right that I can pull that scalar multiple out. So c times t of p, well, we already evaluated t of p to be a naught. And so t of cp is going to be, well, if I distribute the c through the p, I get can x to the n plus c a1x plus c a naught. And again, as always, if I actually evaluate that, sorry, I need to actually put the t in there still. All I've done is simplify it a little bit. So now when I actually do t of this polynomial, I'm going to plug in 0. And so I get can times 0. Everything here is going to have a 0 attached to it. And all that I'm left with is that ca naught. And so I get ca naught, and it's the same thing as the other one. So both the properties that I need are true. So like, yes, this is a linear transformation.